Hello, this is the first lecture of the set of 20 lectures on calculus of variations. This lecture I will start with the introduction of calculus of variation. Here in this I will be following the reference book. The books. This is calculus of variation. With applications. In the set of 20 lectures on calculus of variations, we will be covering many aspects of calculus of variations, how the study of calculus of variation started, and what are the applications of the theory developed for this. That is what we will be discussing in this. So, in this first lecture, we will give some introductions of problems arising in calculus of variations. The study of calculus of variations started in 1696 by John Bernoulli. He proposed a problem which is known as Brachester-Krohn problem. In this problem, what he proposed, to find path along which a particle slides under gravity, then it takes the least time. So, mathematically this problem can be stated like this, that in a vertical plane you have 2 points A and B, not at the same level, at different levels, and then if you join this by a smooth curve like this, and a particle slides from A to B under influence of gravity, then certainly the time taken by this particle from coming from A to B is function of this y, where y is this curve as a function of x. So, this is the x axis and this is y axis, and this y is a function of x, smooth function of x, so that at each point the tangent is defined. And so, here this time taken by the particle under the influence of gravity in sliding from A to the point B is denoted by Ty, and this will be given by certain integral. Here let us say this is the point x1 and this is the point x2 here. So, this point is x1 y1 and this point is x2 y2. Then the integral is from x1 to x2 square root of 1 plus y prime square upon this the ds distance upon the velocity which is a function of y, and this functional is what called the time taken by the particle sliding from A to B under the influence of gravity. Here this time here will be actually given by this integral x1 to x2 square root of 1 plus y prime means dy by dx upon the velocity. Here this is actually can be seen, this is like integral from x1 to x2 ds upon the velocity, that is what will ds is the element arc length along this curve. So, that ds the time taken from this point to this point. So, in this element area ds upon the velocity, that will be the time taken by this particle coming from this point to this point. Now, here, so if this total time taken by this particle from A to B will be given by the integral x1 to x2 integral of ds upon v. So, ds is actually square root of 1 plus y prime square, and the velocity v will be taken as a function of y. So, that is the time taken by the particle from sliding from point A to B. Now, this is what is called the problem of Rochester-Krohn, and we are asked to find a curve along which this takes the least time. So, that is what is called the problem of quickest descent. Quickest descent. So, we have to find y such that time taken in sliding, time taken by the particle in sliding under gravity from A to B is least. So, this is the problem of Rochester-Krohn. Now, this problem was proposed by the famous mathematician John Bernoulli, and it was in the same year 1696 was solved by several mathematicians like Newton, Lebanese, Weierstrass, and John Bernoulli himself, and some other mathematicians of that time. So, that the problem of calculus of variation started with that. Now, there are many other problems which can be posed as the problem of calculus of variations, like you have in a plane, suppose you have 2 points A and B, and then the length of the curve, this is the function y of x. We know that the length of this curve is given by the integral x1 to x2 square root of 1 plus y prime square dx, which is again actually given like x1 to x2 ds. So, again here ds is the element area, element length in terms of arc length s. So, integration of this ds element length from x1 to x2, here again this is point x1 and this point is x2. So, this is x1 y1 and x2 y2. So, this is what this integral x1 to x2 square root of 1 plus y prime square dx, which is nothing but the integral of ds element length x1 to x2. So, this gives the length of the curve y. So, this is a function of y. If we change y, then its length will change. Now, the problem of calculus of variation in relation to this is to find the curve such that the length is least. So, we know the answer is that the straight line joining these 2 points will be having. So, a straight line joining A and B has least length. But how we prove it mathematically? Again, it is a problem of calculus of variation. And next problem can be thought as supposing you have this surface area double integral over d, then you have surface area ds, now which is bounded by so this surface area over d. So, this what is the smallest surface area, I mean the curve is given to you, and then here let us say this is S surface bounded by this curve, and now this length of the curve is fixed. Now we want to find what is that surface which will have the least surface area. We know that it will be that flat area if it is a plane curve. So this is also a problem of calculus of variations. Now, so with this, here the other problem of surface of area for a given surface zxy, it can be written as double integral d square root of 1 plus zx square plus zy square dx dy. So here we have to choose that surface S surface zxy such that this has least surface area. So this is also a problem of calculus of variations. Now here this is certainly a generalization of a minimization or maximization of a curve, where you want maximization of points at which the function has minimum or maximum. For example, here if you consider this curve, so let us say this is the point A and this is the point B here. So this f is defined from A to B into x, A to B into r, and this function has it's at least continuous, and we may like to have more smoothness property on this function, like differentiability at all points in the interval a b. Here we can see that this at this point f a is maximum of f x between A to B. So f a is the maximum here, and f b, similarly f b is minimum of f x between. So this is a global maximum, f a is global maximum and f b is global minimum. Then there are other points like this. Let us say this is point x1 and this is point x2, this is point x3. So here in this f of x1, similarly f of x2 and f of x3. Now these are the points of local minimum or maximum. So for example, this is local minimum, because in the neighborhood of this, here this has the least value. Similarly, in the neighborhood of x2, here this has the maximum value. So this is local maximum. Similarly, f3 is also local minimum, but we have this f a as global maximum and f b is global minimum. So at these points here we can see that the if the function is smooth, if it does not have corners like this, if it is a smooth function like this where the derivative exists, then we can see that here derivative becomes horizontal. Similarly, the tangent becomes here horizontal. That means derivative is 0. F prime at this point x1 is 0, f prime at x2 is 0. So f prime at x1 equal to 0. Similarly, f prime at x2 is 0 and f prime at x3 is also 0. So these are actually if the function has continuous derivative at all points in the interval a to b, then we can see that at these local minimum or local maximum we have the derivative of these functions becoming 0. So here given a functional like this, so we have a functional, for example here L of y, where L is a function from the function space. So we call it the admissible function class from here interval a to b. So, this into R, where A is the admissible class, A is called the admissible class of functions. So, Ly is actually called functional. So, Ly, L is for each y here. So, each y in A B, A to B, we have associated Ly, which is a function in, which is a number in R. So, given a function in this admissible class, this L which is called functional, which is a function of function loosely speaking. So, here given any, so here the argument of L is a function actually, whereas in the previous case here this F was from number to number. Here in this case L is a from a given function to a number. So, it associates a function to a number. So, such a thing is called functional. So, L is called functional. For example, this length of y given by this x1 to x2 square root 1 plus y prime square dx. This gives you the length of y. So, L for a given function continuously differentiable from the set or from the function space, we call it C1 x1 to x2 from the space C1 to C2. C1 means continuously differentiable, the set of the space of all continuously differentiable function from the interval x1 to x2 into R. So, this is the space of all continuously differentiable function. It is a usually we will consider Ck, k being integer, non-negative integer, Ck a to b, which will denote the space of all continuous functions whose kth derivative will be continuous. So, for k equal to 1, we will call it C1 x1 to x2, and the values are real numbers. So, we are considering only the real valued functions here, and so an element here will be called an admissible function here. So, this is the admissible class like a comma b. So, here this a is x1, b is x2, and this a here is actually C1. So, that is the class of that is the admissible class of functions for this functional to L to be defined here. So, here in this case for any given function y from this space, L assigns a number Ly. So, that is what is the actually functional, which assigns to each function y in this space, admissible space of functions here, for this functional to be defined. If we have higher derivatives appearing here, then we will take higher order function spaces here. So, this for given y, the length of y will be given by this integral here. So, if we change for example, here you have this x1 x2 here. So, this is the point a x1 y1, and this is the point B x2 y2, and this is the curve y x here, which joins these 2 points A and B. So this functional will give the length of this y. If we change this, let us say this is y1, if we consider the another function y2 here, so then we will L of y1 will be given by integral x1 to x2 square root 1 plus y1 prime square x dx. Similarly, L of y2 will be integral x1 to x2 square root 1 plus y2 prime x square dx, like that. So we change this y, this L will be changed. Now we want to find what is that y for which we get the least number, which will be the least length, the length of the curve for joining these 2 points A to B, such that its length is the least one. We know the answer that it has to be a straight line joining these 2 points, but how do we prove that? So that will be a problem of calculus of variations. So now before going into the calculus of variations, we need to develop certain tools for that. Similarly, we will be having this higher order. So here the functional will be of this type, like the integral I going from x1 to x2, certain function x, certain function f, which is function of these variables. X is an independent variable, y as a function of x, and then dy by dx, that is y prime x dx. Now again here this f is function of 3 variables x, y and y prime. So here and these functions, like these arguments, of course x is an independent variable which is varying. So x is lying between x1 to x2, and y is a function from x1 to x2 into R, such that y prime and y being c1 x1 to x2, like this, so that y prime will also be a function from x1 to x2, and it will be continuous, so that y prime is continuous here, and this f is continuous of all its arguments. So there are 3 arguments for this function x, y and y prime, and here this f is a continuous function of this variable, and this, and y in turn is continuous function between x1 to x2, and y prime is also a continuous function. So overall this integrand becomes a continuous function from x1 to x2, and then by this Riemann hypothesis we know that this integral I exists as a Riemann integral. So here the problem of calculus of variation is then to find a y, function y, so that its derivative is also continuous, and this value is minimum or maximum. So we call such a thing as optimum value, optimal value, and y we call as optimal curve for, or extremal. Y is called extremal, and this integral I will be optimal. So these are the terms we use, that what is that extremal for which I is actually having the value, extremal value. So such functions y which are from the admissible class, here admissible class is C1 class of functions from x1 to x2 into R. So here the generalization of this could be like I x1 to x2, and f has more variables now, like x, y1x, y2x, and similarly this y and x, and then their derivatives y1 prime x, y2 prime x, and so on up to yn prime x dx. So this is the generalization of this. So this can be treated as a particular case of the more general problem, where again you have these y1, y2, yn, they are from the admissible class, like we are considering here derivatives. So the derivatives should be continuous here in order this integral to exist as a Riemann integral. So here f will be actually a continuous function of all these arguments, and these x is an independent variable here, and y1, y2, yn, they are dependent variables, and these derivatives are also appearing here. So again the problem of calculus of variation is to find these functions y1, y2, yn, and such that this integral has either minimum value or maximum value depending upon the problem posed here. And in addition to this, like we have in this case we have the curve joining these 2 points a and b. So here the condition is that it should pass through x1 y1 and x2 y2. So that means here y1 at x1 should be this y1 here, or y at, so if y joins this, so this y at x1 should be y1. Similarly, y at x2 should be y2, so that this curve passes through those given points. So and these points are fixed here. Similarly here this y1 x1 must be some given value, like so again you have several curves y1, y2, yn, and they should pass through these given points a and b. So this y1 x1, there will be conditions on this, like you have y1, similarly y1 x2 will be y2, and so this should be for all those y2 x1 will be rather y1 y1 0 you can put here, y1 1, y2 at x2 is y2 1, and so on. You have yn x1 as yn 1, and yn x2 is yn 2 here. So these are the additional conditions to be satisfied, so that the curve pass through those given points here. So further generalization could be here you consider higher order derivatives. So I, again it will be, so in the previous case this I is a function of y1, y2 and yn, and here in this case let us say I is a or special case, like you have I as y only, but then you have higher order derivatives appearing x1 to x2, f of x, y, y prime, y double prime, and up to y nth derivative is appearing there. So like this. So again here the curve y is expected to, it is passing through those given points a and b here. So this is y x, and it has more smoothness now. So, admissible class has to be Cn x1 to x2 . So, y has to be actually in this space of functions Cn. So, up to nth order derivative should exist, and it should be a continuous function from x1 to x2. So, again here you will have certain additional conditions like y at x1 is y1 and y at x2 equal to y2 like 0 0, and then y prime at x1 is something y1 1, y prime at x2 is y1 2, and so on. There will be up to yn minus 1 at x1, yn minus 1 1, and yn minus 1 at x2, yn minus 1 2. So, these are additional conditions given, so that this y has to satisfy all these conditions, and it has to optimize this integral depending upon whether to minimize or to maximize. Then further generalizations could be like I y. Here you have more independent variables. So, for example, you have let us say 2. So, then you will have double integral, and f is function of let us say x1 x2, and then some function z of x1 x2, and then del z by del x1 x2, and del z by del x2 x1 x2, and dx. Here you have two dimensional situation here. This is x1 x2, and there is some domain D here, and on this z is the surface given like this. So, this is the surface z equal to zxy. So, for given any point here, this is the value zxy. So, xy here, this is z x y and zxy. This point is x y and z xy. Let us say this is z here like this. So, here this function f is a smooth function here of all these arguments, and this zxy is denoting this surface here. So, in order here again the problem of, sorry, this should be z here. So, this integral I is a function of z. If you change this surface, this value is going to change, and we need to find that z such that it actually the boundary is fixed here. So, along this z will be satisfying certain boundary condition, that z has the fixed boundary here, and that z is actually optimizing this functional. So, that is the condition of, that is the problem of optimization which we will be considering here. So, we will be considering these many such cases where we will have one of these situations here. Now, we will consider certain preliminaries of the concepts which will be required subsequently. So, we start with preliminaries. So, here we had been considering continuity of a function. So, what do you mean by that? A function f from this x1 to x2 into R is called continuous if continuous at x equal to x0 if this limit x tending to x0 of f(x) exists and is equal to f of x0. For example, here if you consider this function, so here this is x1, this is x2, and then there is some point here x0 here. So here you can see that let us say if we consider this is a straight line, except at that this point x0 function is not defined here, so it cannot be continuous because it has to be defined at that point. So let us say at this the function is here. So at all these points function is like this, and here all these points on the right the function is like this up to x2, but at this point x0 this value is here. So this is although the limit extending to x0 exists, and here that will not be equal to the value of the function which is actually this. So this is a discontinuous function. Again, the other example is, suppose the function is 1 here and this point onwards 2 here. So here up to 0 to 1 the value is, so f(x) equal to 1, 0 less than x less than 1, and it is 2 for 1 less than equal to x, and let us say up to 2, 1 to 2. So this function is discontinuous at this point. Here the left limit exists, right limit exists, but that is not equal to the value of the function here. So the left limit here is 1 at this point. So f(x) limit x tending to x0 minus, that is what. So this limit x tending to 1 minus means if you approach this point 1 from the left side, so this will be actually equal to 1, and if you take limit x tending to 1 plus, that means you approach from this side, so of f(x), that we know that we are approaching from this approaching to this point from this side like this, so it will go to 2. So these two are not equal, and therefore this limit does not exist, and therefore the function is discontinuous, which can be seen intuitively also from this figure that there is a discontinuity here. Although here in this case it is not so apparent here, but then we can see that if we approach to this point from the left, then it is going to this value here, and similarly if we approach to this point like this from here, so values are approaching along this and it is going to this. So these left limit and right limit, they are same, and so limit exists, but it is not equal to the value of the function, which is also a condition for continuity here, because f of x0 is here, f of x0 is here, which is not here. So therefore there is a discontinuity. So these kind of things should not happen for a continuous function. So these are the concepts of left limit and right limit, and the value of the function, they should all be equal. So then we say that the function is continuous. When discontinuity can occur in many ways, but we will be considering only discontinuous functions of the first kind, so that here what we have only jump discontinuities like this. So in this case we have left limit and right limit exist, and they can have the difference here. So that difference is called the jump here. At this point the jump is this: from the right we are approaching to this point, and from the left we are approaching to this point here. Therefore, there is a jump discontinuity here. So that is what is called the discontinuity of the first kind. The discontinuity of second kind, where the limit does not exist at all, one of the limits left or right does not exist, such a thing will be called discontinuity of the second kind. We will not be considering such functions, we will considering only the functions having only discontinuities of the first kind, so that they have jumps at finitely many points. So such functions are called piecewise continuous functions. So we have piecewise continuous function, so these are the functions like you have left and right limits existing in the interval like this x1 to x2. So here this is the point of discontinuity, this is the point of discontinuity here. So let us say at a and b in the interval x1 to x2, here at this point there is a jump discontinuity, and there is here also there is a jump discontinuity of this. So we can have finitely many in any bounded interval like x1, x2, there are finitely many points of jump discontinuities. So there are only, like in this interval, there are only 2 points here at this point, and this at the point A, and at the point B there are jump discontinuities here. So this is a piecewise, this is an example of piecewise smooth function. So in any interval of finite length, there should be only finitely many points where the function can have jump discontinuities. So such a function is called piecewise continuous function. Similarly, we will have the piecewise differentiable function. So piecewise differentiable function means here you have the function will be continuous function is continuous on x1 to x2, and f prime is piecewise continuous. So that f prime has only jump discontinuities at finitely many points in the interval x1 to x2. So such a function is called piecewise differentiable if it is if the function is continuous on x1 to x2 and f prime has left derivative and right derivative existing at all points, and there are only finitely many points where they differ. So and it will eliminate the case of the points where the left derivative and right derivative are not equal. Only if they are equal, then it will be actually equal to the value of the function. So there there cannot be a case in this that the left derivative and right derivative are equal, but they are not equal to the value of the derivative, the value of the derivative at that point. So such a case will be avoided in this case, because function is continuous, and if the left derivative and right derivatives are equal, then the derivative at that point will also exist and it will be equal to the value of the function. Next we will be considering partial differentiation and total differentiation. Here we consider a function u as a function of several variables u, let us say x1, x2, xn. So for u here, this u is from Rn to R, or in certain domain which is in a subset of Rn, and the values are real numbers here. So and these x1, x2, xn are in turn, and this x1 or xi is function of let us say T1, T2, Tm. So then we will be considering this del u over del Ti. It will be actually del u over del x j, and then del x j over del Ti summation over j equal to 1 to n. So j is running from 1 to n, and this I is running from 1 to m. So this I equal to 1, 2 to m. So these are the partial derivatives. Here u is a function of several variables x1, x2, xn, and these xi's in turn are functions of some m variables t1, t2, tm. Then the partial derivative of u with respect to these variables ti's will be given by this kind of chain rule, summation j equal to 1 to n del u over del x j and del x j over del Ti, and summation over this j going from 1 to n. Now if in particular if this xi's are, so in particular if xi's are just function of one variable xi of t only, then we can have, then this derivative will be total derivative like du by dt, and you have this summation del u by del x j and then dx j by dt, then j equal to 1 to n. So this will here, then this u itself becomes a function of single variable t, and therefore this partial derivative reduces to ordinary derivative, that is known as total derivative here. Although u is a function of several variables x1, x2, xn, but these xi's are now in this case function of a single variable t, and therefore u is a function of single variable t, and we get du by dt as the total derivative in this case. Now the next one would be differentiation of integral. at several places we will have the integrals coming into our picture as functionals, and we will be required to differentiate it with respect to its arguments appearing in the integrand. So here, like I of certain variable t, integral x1 function of t to x2 of t, and f, let us say x and t dx. So this is x is the variable of integration here, and this has limits x1 x2, but these f as well as these xi's are functions of t. They are continuously or piecewise differentiable functions of t. Then this di by dt is given by the Lebanese rule, it is called, that is also denoted in short I prime t, which is f at the upper limit you have x2 t t, and then dx2 by dt minus f at x1, which is a function of t dx1 by dt, and then plus integral x1 t x2 t and del f by del t of x t dx. So this is what is called the Lebanese rule, which can be seen by the first principle. I prime t will be actually, see here it can be calculated by this, what is I prime t? I prime t is by definition it is limit t tending to or h tending to 0 I t plus h minus I t upon h. So we can apply this here. So we will have this I t plus h, where t will be replaced by t plus h here, x1 t plus h, x2 t plus h. So that is what we will have. I t plus h will be given by x1 t plus h to x2 t plus h, f of x t plus h dx, and then subtracting here. So I of t plus h minus I of t will be x1 t plus h, x2 t plus h, f of x t plus h dx minus x1 t to x2 t f of x t dx. Then here we will break it into two parts, x1 t plus h to x1 t, and then so this first integral can be written as x1 t plus h to x1 t and f of x t plus h dx plus x1 t to x2 t f of x t plus h. So this you can take with this minus f of x t dx, and plus then you have x2 t to x2 t plus h f of x t plus h dx, and then dividing by h here. So we get 1 by h here, 1 by h here, 1 by h. Then letting h tends to 0, we get the first term by this, that the second term with the, because this we will write as minus of this thing. The first term we will write it as minus 1 by h x1 t2 x1 t plus h f of x t plus h dx, and this the last one is anyway here as it is x2 t to x2 t plus h f of x t plus h dx, and the middle one will be that 1 by h of x1 t to x2 t. This 1 by h we will take it inside, and then f of x t plus h minus f x t dx. So, 1 by h taking inside and using the continuity or differentiability property of f, we can see that the last term here, this one will be given by, which will give you the partial derivative with respect to t here, like in this one, and this term with that minus sign here is the this limit of this, and the first term will be the limit of this. So, we get the this is what is called the Lebanese rule of differentiation of the integral. The next tool will be the integration by parts. Thank you very much for viewing this lecture.